This is question number 31 in chapter 7. The question reads, in a ballistic pendulum experiment, projectile 1 results in a maximum height h of the pendulum equal to 2.6 centimeters, and a second projectile causes the pendulum to swing twice as high. H2 is equal to 5.2 centimeters. The second projectile was how many times faster than the first? So here I've made a sketch of the concept of the ballistic pendulum. You have some ballistic here, some bullet gets lodged into the pendulum, which then causes it to swing up here to this upper position. So the pendulum is tied to this string right here, and it just kind of swings up. And so these types of problems involve a conservation of momentum in the collision right here. So this is a collision, and you'll use conservation of momentum techniques to basically solve for it. And then the second part of the problem involves a conservation of energy. So you have the bottom of this block, this much heavier block here, rises to some upper position here, and it's this difference in height h that's a conversion of kinetic energy that it has. Of course, this kinetic energy is the final velocity after the collision in part 1, and then it reaches some gravitational potential energy at its maximum height here at kind of position B, if you will. And so you're going to solve kind of part 2 by looking at the conservation of mechanical energy. So this is kind of a two-part problem. Let's go ahead and start with part 1. Part 1 looks at the collision using conservation of momentum. Okay, so we can start these types of problems by saying that the sum, oops, that was an ugly sigma, the sum of the momentum in the system initially must be equal to the sum of the momentum in the system finally. And so therefore, I have two things in the system. I have the momentum of the bullet, which I'll call lowercase b, plus the momentum of the block, which I'll annotate with a uppercase b in my subscript. And this is before the collision. On the right-hand side, I have the momentum of the bullet after the collision plus the momentum of the block after the collision. We know that the momentum of the block before the collision is 0 because it's not moving. And in the next step, I'll basically take each one of these terms and separate them out into their parts. So I have mass of the bullet times the velocity of the bullet is equal to the mass of the bullet times the velocity of the bullet after the collision plus the mass of the block times the velocity of the block after the collision. Of course, this is an inelastic collision. So in an inelastic collision, we understand that the velocity of the bullet after the collision must be equal to the velocity of the block after the collision because they hit and stick together. And so therefore, I shouldn't be using separate variables to describe the same number. Let's call that VF. So I'm going to basically substitute each one of these terms, velocity of the bullet and velocity of the block, with V sub F. So that gives me mass of the bullet, mass of the block times VF. Nothing has changed on the left-hand side. And on the right-hand side, I can factor out VF. And so I now have mass of the bullet plus mass of the block, or the total mass of the system, times my final velocity here is equal to mass of the bullet, velocity of the bullet before the collision. Finally, I'll divide both sides by this in order to isolate VF, and so I'm left with an expression that looks like this. The final velocity of the combined bullet-block system is equal to the mass of the bullet times the velocity of the bullet before the collision divided by their combined mass. Now, I could write it as m sub t for the total mass, but I'll leave it in terms of mass of the bullet and mass of the block together. Okay, so this is something that you'll see an awful lot in these types of problems and other inelastic collision problems. This kind of handles the expression for the final velocity of this block the instant after the bullet lodges in it. So we have something that looks like this. The bullet comes and hits it, and it's got some initial velocity here at that moment. And that's this kinetic energy now that we're starting with in part 2 of the problem. This is the important piece for part 2. Part 2 involves conservation of mechanical energy. So we know that mechanical energy is conserved in this pendulum. We can say that the kinetic energy that it has at this position, and just to make this a little bit easy, let's call that position A and let's call that position B. So the kinetic energy at position A is equal to the gravitational potential energy that it has at position B. And now I can basically write this as 1/2 mv at A squared is equal to mgh at B. Immediately we can see that the masses cancel out, and perhaps more importantly, I can see that this expression is going to end up working its way in here. So I have the final velocity after the collision, which happens to be the initial velocity here that constitutes its kinetic energy. I'm not going to make that substitution just yet. Let's go ahead and finish this expression over on the left-hand side. So I'm going to get that the velocity at B is equal to, the velocity at B squared is equal to 2gh at B. Of course, if I were trying to solve for h, which I'll go ahead and do here, I'm going to get the velocity at B squared divided by 2g. And so now I have this expression that will determine the height based on how fast it was going. And I know how fast it was going in terms of the initial velocity of the bullet and the mass of the bullet in the block, so I could substitute that in. So what I've written so far is kind of like a general format for solving these types of problems, a ballistic pendulum or some other combination problem where you have conservation of momentum and conservation of energy kind of wrapped up into the same problem. In this particular problem, they want you to figure out how much faster we must have been going if it went twice as high. So we did a test, and h1 was equal to 2.6 centimeters, I think. Centimeters or meters? Yeah, it was centimeters. And in height 2 was 5.2 centimeters, or twice as high. So then the question is, how much faster was V2 compared to V1? So we don't know either of these two. But what we can do is we're basically solving for the velocity of the bullet. In other words, let's go ahead and rearrange this expression for the velocity of the bullet, and that's going to be our expression for these two guys, V1 and V2. So if I do that, I'm going to get something that looks like this. The velocity of the bullet in test number 1 is equal to the final velocity, VF, times the total mass of the bullet in the block. I've simply multiplied both sides by the sum of the mass of the bullet in the block. And now I need to divide by the mass of the bullet. And now what I have here is an expression for the velocity of the bullet. Okay, let's go back here now and take this expression for the final velocity right here. And that's the velocity at point A. So let's take that and say that that's equal to root 2gh, right? All I've done is take the square root of both sides. So the velocity that it had after the collision, the moment after impact with the bullet in the block, is equal to root 2gh. And I'm going to plug that in right here. So I've got a substitution going on here, and now I have an expression for the velocity of the bullet at point 1. It looks like this. The velocity of the bullet at point 1 is equal to root 2gh times mb plus m capital B divided by the mass of the bullet. Okay, so this is an important expression, and it's what we're going to use to solve this problem. Okay, so since I'm looking for the ratio of these two speeds, the velocity of the bullet and the velocity of the bullet in the second test, these are basically the things that I'm looking for. I can say that the ratio of the bullet in case 2, where it went twice as high, over the ratio of the bullet in case 1 is going to be taken from this expression. So now I can say, all right, the velocity of the bullet in case 2 is root 2g 2h, right, because it went twice as high, times mb plus m of the block over the mass of the bullet. And then all of that, this is a complex fraction, is over now the same expression for the velocity of the bullet in case 1, which is going to be 2gh over mass of the bullet plus mass of the block all over mass of the bullet. Okay, so now I can say, hey, look, most of these things show up 2 times. That goes away, and everything in here goes away except for the square root of 2. In other words, I could rewrite this as root 2gh times the square root of 2, which means then that the 2gh goes away, and the root 2gh goes away here. And the only thing that I'm left with is the root 2 in the numerator. In other words, the velocity of the bullet in case 2, when it went twice as high, had to be the square root of 2 times faster. Or I could say this way, the velocity of the bullet in case 2 is equal to the velocity of the bullet in case 1 times the square root of 2. It's 1.4 times faster than it was in the first test in order to get it to go twice as high.